Um, so today, Billy is going to be presenting, and he's going to be walking you guys through a lot of demos and activities. So I'll hand over the presentation to Bill.
All right, thanks. So the first thing I'm going to get you guys to do is go ahead and log on to your machines, because we'll be doing a lot of sort of walk-through demos. So instead of just lecturing to you guys, I'll be showing you a lot of the concepts by doing the demos in Excel, and I'm going to get you guys to follow along, since you'll be using these skills to do your final project later on in the day and tomorrow. So this is about data analysis. So this morning we're going to look at analysis of a single variable. This is probably going to be a review to a lot of you guys, so bear with me if it is. But hopefully you'll learn a fair bit new, and this is very important in order to do our final project, which gets us to why. Why are we doing this? Remember that smart networks can adapt to the demand, but how do they adapt? So on Tuesday, you ran a script to get Toronto traffic data. That's the data from the demand, but that's only the first part of adapting to it. We have to analyze it, and in order to write smart networks to do that, we need to be able to do it manually first. So that's what we're going to be focusing on today. So we will do manually what intelligent infrastructure does automatically in real time. But this does mean math. So I presume most of you are fairly up on math. You fairly like it. It's early in the morning. I get it. But let's jump right in. So some notation. The Greek letter capital sigma means sum. Pardon? Can't hear you. OK. So the Greek letter capital sigma means sum. How many of you guys have encountered this before? OK, so most of you. How about this notation? Any of that ordered set or these subscripts? OK, so we're saying that S is an ordered set. It contains the numbers 1, 2, and 3. And sigma S, then, is 1 plus 2 plus 3 is 6. Does that make sense to everyone? So we can sum over a variable instead. So we can start by setting n equal to 100, or n equal to 0, and increment n to 1, then 2, all the way up to 100, and sum that up to 50/50. Does anyone recognize that problem, summing up 1 to 100? A couple? Yeah, so that's the problem that Pascal was famously given in, I believe, first grade, or the Greek equivalent thereof, not Greek, French. We can do things to each element first, such as we can square it. So if we square 1, then add it to the square of 2 to the square of 3, we get 14. And finally, one last piece of notation is that n of s means the number of elements in S, and that's sometimes called the cardinality. So for everyone on board? Great. So some basic concepts in statistics. This is probably going to be very much review, so I'll go quickly for it. The mean, or the average, is going to be summing up all of the elements in some set X and dividing by the number of elements in the set X. And the residuals, has anyone heard of those before? OK, so now we're getting into some new stuff. So the residual of each datum in X is the difference between the mean and X itself. I should point out this is actually backwards. It should be X minus mu. So that'll give you the negative residual, but we don't really care about the sign at this point, as we'll see. So this gives us the difference it is from the mean. So if it's close to the mean, the residual is going to be closer to 0. If it's farther from the mean, the residual is going to be larger. And it means just the difference between the datum and the mean. So we're going to try this in Excel. So if you guys could open up a new Excel spreadsheet. And the first thing we're going to do, so you can follow along as I do it on my screen, I'll wait for you guys to, I'll get it open. Most of you can that? Kartik? Do you know what we're doing? Yeah. All right. OK.
General engineering, Microsoft Office stuff.
So in cell A1, you're going to type equals RAND, stands for random, and then 2 brackets. And then hit enter. And this is going to enter a random number between 0 and 1.
You need an equal before
Yeah. Yeah, so it's got to be equals rand, not just rand. And then we're going to select that cell, and this little box in the corner click it, and drag it down all the way to A10. This generates a column of 10 random numbers. Has everyone got that so far? Can I get the counselors to sort of come around and make sure that, or help people who are having trouble? So put your hand up if you're still having some trouble. Mm-hmm. You need an opening bracket and a closing bracket.
Oh.
Then hit enter and you got it.
Oh.
Okay? So, Hannah, you need an opening bracket and a closing bracket at the end of it. And you're good.
How many columns do you have?
I have 10. You guys can go more if you want. I'm just doing 10 to make it quick. If you want to do 1,000, that's fine if you can keep up. Yes. Pardon? Let's see what you have. So you have, that's good. So we have this box here. Click it, drag it down.
Oh.
All right, try that yourself. So put your hand up if you're still having trouble. Has everyone got a column of 10 random numbers? All right. So now what we're going to do is we're going to type in cell A12 equals average and then an opening bracket. So this is the Excel function to calculate average, and opening bracket tells us that after it we're going to put what the average is going to be of.
So we're finding mean average, or?
Yeah, so average and mean are the same thing in this context. And then after that opening bracket, we're going to type A1 colon A10. This is going to tell Excel that we want all the cells between A1 and A10. It'll then calculate the average of that. And then, yes, you need a closing bracket at the end of that. Once you've entered that, you can hit enter and it will calculate the average. Has everyone got that? Put your hand up if you're having trouble. Great. And you can hit F9, and what that will do is that will reseed the data, which means it'll calculate more random data, which will calculate a new average, and you can see it change as it does that. And you'll note that if you keep hitting F9, the average tends to be close to 0.5. That's because the data are between 0 and 1, so it makes sense that when you average 10 of them up, it'll be close to the midpoint between that. How are you guys doing, John and Jordan? Are you okay? All right. So now in cell B1, we're going to enter equals A1. So this is going to set it, A1 is a reference to the value in cell A1. Okay? Equals A1 minus, and then a $sign, A, another $sign, 12. So that's going to reference the value in A1 and the value in A12 and subtract the 2. What the $signs do is they prevent the value from changing when we pull it down. So for those of you not familiar with Excel, I'll show you. If we hit enter and pull it down as we did to get the first column, you'll notice that we have A1 minus A12, A2 minus A12, and so on. So the 1s, 2s, 3s change because there's no $sign. The 12 stays the same. Have we all got that part done? Anyone having trouble? Great. And so the last thing we're going to do is make a plot of these residuals. So note that these are the residuals. These are the value minus the mean. So to make a plot, we're going to select these 10 values, go to Insert, Charts, and then under Line, choose the first 2D line. Does everyone see which one to go to? Insert, Charts, Line, 2D line. Your screen might be a bit bigger, so you might see it expanded out like this. In which case, you go like that. Then lines, let's see what your screen looks like. Yeah, there you go. So make sure So you have to calculate the data in B first. So see that cell there? Click on B1 and pull it down. Yes, it does. That's a good point that you brought up. It does change value because the rand function generates random numbers, and it regenerates a new random number every time the spreadsheet updates. Or if you press F9, you can force it to do that. So what we should see once we've generated this chart is the residual plot, as it's called. This is a plot of the difference between the data and the mean. So I'm noticing most of you have it. Some of you are plotting it with the original data. That's good. Anyone still having trouble? All right. So guys, are we good to move on? You okay there, Solomon? All right. So it makes sense that the larger these residuals are, the farther the data can get from the mean. Does that make sense to everyone? Yes?
Why are there negatives?
There are negatives because some data are larger than the mean, some are smaller, right? Because the mean is halfway between, or not halfway between, but the midway of the data. So some will be larger than it, some will be smaller. If they were all larger than it, then the mean would increase. Okay? Right, so residuals can be both positive and negative. So the magnitude of these residuals indicates the spread of the data, how spread out it is from the mean. And we can quantify this. So let's head back to our Excel sheet. And I'll make it half screen again so you can see the slide. So we're going to first square each residual to make it positive. And we're going to do this by heading to cell C1. Okay, whoops, if it does that, just hit or backspace out and hit enter. And now we'll head to cell C1. And we're going to type equals B1, then the caret symbol, 2. So that caret symbol means to the power of, so equals B1 squared.
Shift 6.
Yeah, it's the shift 6. And then if we hit enter, it's going to square that residual value. And we can then click on it and pull it down to create 10 more squared residuals. Pardon? Yeah, so to square it, we're going to put equals B1 and then shift 6, so the caret symbol, 2. Yeah, you can see it here in my formula box, that B1 shift 6, 2. Does everyone have that so far? Does everyone have a column of 10 squared residuals? Put your hand up if you don't. All right. And so now, yes. Okay, yeah. So you've got, head up to the first one. So the first one we want to be B1. Yeah. Now pull that down. There you go. Now what we can do is we can sum up over all of these squared residuals. So it makes sense that the greater the squared residuals are, the farther spread out the data are from the mean, right? And the reason that we can't just sum up the residuals themselves is because, as Kartik mentioned, they're both positive and negative. If we sum up the residuals, they're actually going to equal 0. So when we sum up the square residuals, the way we do that is we're going to type equals sum, opening bracket, and then we can type C1 colon C10. We can also click on C1, drag down to C10. So that's another time-saving trick you can use with Excel. So that's what we want to have typed in there, and when we hit enter, that will calculate the sum of the squared residuals. How's everyone doing on that? All right, put your hand up if you're having trouble. Good. So, in the mathematical notation that we covered initially, this is equal to the sum of x minus mu squared, right? Does everyone understand why that notation applies in this sense? You can't see it? Okay, so it's, I'll make it bigger. All right, Solomon, can you see now? Right, so the sum of x minus mu squared. And note that the squared happens inside of the sum, right? Not sum of x minus mu squared. So I'll head back to our quarter screen view. So this increases with n, right? The more squared residuals we have, the greater we're going to increase our sum of our squared residuals. But we want an indication of the spread of the data that doesn't matter how many data we have, right? We want it to be based on per datum instead of overall. So to do that, we normalize by dividing by n. And this quantity is known as the variance. So variance, you know that variance like variation means how varied it is. So in the case of statistics, it means how spread out it is. And it's in squared units of x. So do you guys understand what I mean by squared units of x? So if we head back to our Excel sheet, we have, if this is in meters, so if we have, say, 0.77 meters, then we take the residual, we're subtracting a meter value from it, and when we square it, we're going to get meters squared. And the sum of that will also be meters squared. And so we can divide by n, as we mentioned. So we're going to type in C13 equals, and then our sum of squared residuals, C12, divided by, and how many, what's our n value for this data set? Right, 10. And so finally, as I mentioned, the variance is in square units of x. So to get the standard deviation, we can take the square root. And to do that, we'll type equals SQRT. And then inside the bracket, we'll put that sum of squared residuals divided by n. And that value there gives us our standard deviation. OK, so I'll show it up on the screen. So we have our sum of squared residuals, which you should all have. And then we take that, divide it by n. In this case, n is 10. And put that in some cell that's below it is easiest. And finally, we're going to take the square root of that cell. Does everyone have that? Put your hand up if you don't. So we're going to type equals SQRT, and then we'll put C13 or whatever cell it is that you have the sum of squared residuals over n. Pardon? Yes, inside the bracket. Right? So if you type exactly what's here, that will give you the square root of whatever's inside the bracket. Right? You can play around with that if you want. You can type equals SQRT of, say, 4, and it'll give you 2. Anyone still having trouble? Right, you notice that when I delete it, it reseeds the data. And you can again hit F9, see how the standard deviation changes. So if we take our mathematical notation, which, Solomon, I guess you'd have trouble seeing that as well. This here. OK. So in summation notation, the standard deviation, which we call sigma, this is the lowercase Greek letter sigma, is equal to this sum of squared residuals divided by n square rooted. Now you'll notice I have n minus 1 there. That's because there are actually 2 standard deviations that we worry about. For the purpose of this course, we don't care which one we use. So since Excel uses the n minus 1 one, we're going to go ahead and change that to over 9. So since n is 10, n minus 1 is 9, we divide by that, and that's going to give us a slightly larger value. And we can check that this is correct. So in Excel, the standard deviation is given by Stdev, so we can type equals Stdev, and in our bracket, we now want to reference the original data. So that's cells A1 through A10 inside the brackets, then closing bracket and hit enter.
The PowerPoints are also in the shared folder. Okay? So if you can't see one of the equations, please go to the shared folder. Courses, Deep, Billy share, there's data analysis presentation. We're on slide 6.
Okay, so does everyone have an Excel standard deviation value that's equal to the one that you manually calculated? Oh, sorry, A1 colon A10. Yeah, so you want to reference your original data. And does everyone understand what we've done so far? Pardon?
Should label the columns to make it easier.
I'm
getting confused with which one's this.
Okay, yeah, I'll do that. All right, so I've labeled the columns. So column A contains your original data, column B contains the residuals, and column C contains the squared residuals. Is anyone still having trouble with that? Does anyone not have the manually calculated standard deviation and the Excel calculated standard deviation? If you don't, put your hand up. Okay, so you're going to type equals Stdev, opening bracket, A1, colon, A10. Yep, closing bracket. There you go. And that should be equal to your manually calculated value. Let's see what you've done there. So you got the sum correctly. You divided by 10, and you take the square root. So the one difference is you're taking the square root of C12. You want to take the square root of C13, right? That's where you have it divided by n. And the second thing is, since Excel uses n minus 1, change that over 10 in C13 to over 9. Okay? And then you should have it. Is anyone else having trouble? How are you doing, Solomon? Do you have it? All right, it looks like most people have started to get that, so if I can get Francis and Will to catch anyone else up. And we can move on to the actual analysis. That was just the ugly math part of getting some numbers that we're going to use. Now we can start looking at these numbers and figuring out what they mean. So speaking of mean, the mean, mu, measures the center of the data. Since the mean, or the average, is going to be where the data are centered around, we call that the measure of center. And the standard deviation, sigma, measures the spread. The larger sigma is, the more spread out the data are. So one thing you can try is we have our values between 0 and 1. If we change one of these values to something way out of that range, like 9, look at what sigma does. It jumps from 0.2 to 2, right? So we have that one datum that's way spread out from the mean, and that causes our sigma to jump way up. So as we can see, sigma is sensitive to values that are very far spread out, and we'll get back to that in a minute. And the third characteristic of a data set is shape. So what do I mean by shape? Well, let's take a look. So is everyone done with calculating sigma? Anyone need more time? All right, so we're going to move on to the next activity. You can close out of that or save it if you want. And head over to your shared folder, and you should see a single var analysis file. So we're going to go ahead and open that up. So I already have it open, so I'll head over to it here. Does everyone have a file open that looks like this? Good. So, has anyone heard of or been taught about histograms before? Yes, no, little bit? Okay, well, we're going to learn about them today. So what a histogram does is it tells us how frequently each range of data occurs. So let's take a look at the initial data here. We have 0, 0.1, all the way up to 1, and then we repeat that again. And if we look at these counts in column E, we have 2s in each. So that means that there are 2 data points between 0 and 0.1. We're not actually including 0 here. That's why it's only 2 instead of 4. And then we have 2 between 0.1 and 0.2, etc. So if we go ahead and change one of these, say change one of the 0.1s to 0.3, we see that these values change. There's now only this one value between 0 and 0, or between 0.1, but we have 3 values between 0.2 and 0.3. Does that make sense to everyone? OK, so we're going to change one of these values. So I've changed this one, which was originally 0.1, and we're going to change it to 0.3. And we note then that this number here, so maybe I should point out that columns C and D give us the range. So C1 and D1 are the range 0 to 0.1. And then cell E1 tells us how many values are in that range. So we have one value in that range, which is the 0.1 down here. And then if we go down below that, there are 2 in 0.1 to 0.2. So this one and that one. Sorry. And there are 3 in 0.2 to 0.3 because we have the 0.3, 0.3, 0.3. And that happens because we changed this 0.1. That make sense? So does anyone not understand what column E is telling us? Right? So column E is telling us how many data we have in each range, where the ranges are defined in column C and column D. Everyone doing OK on that? So let's take a look at our columns K, L, M through P. And these columns contain various different data. So we'll first look at column K, and this contains completely random data. So we're going to copy it into column A. Column A contains the data we're actually analyzing. So to do that, we can select it and right-click Copy, and you should see that it shows up in this flashing border. And to paste it into column A, you can go to cell A1, and it's easier in Excel 2010 to hit Control-V, and that will paste it. OK? So we're going to copy column K and paste it into column A. I'm noticing most people have done that. Robbie's playing around with some different columns there. Anyone having trouble with this? So, yeah, you can go ahead and delete that. That's fine. So you'll notice that we now have these two things that occur. One, these dots all show up, and two, this chart changes. And if you look at these dots in this chart, you'll notice that they actually have the same values, right? This is a dot plot, and we have one dot for every two values inside of each range as defined in column C and D. And this down here is what's called the histogram, and it's just a different way of plotting how many values we have in each range. Does everyone have that? Does everyone understand that? Put your hand up if you don't. Good. So we have some random data. This is completely random, and therefore we see a fair bit of fluctuation in our histogram, but it appears to be evenly distributed, or approximately evenly distributed, right? It doesn't make sense that we'd have half our data between 0 and 1, or between 0 and 0.1 if it's random.
Did you do F9?
Pardon?
F9?
Yeah, I don't know if you can. Yes, you can do F9. So if you hit F9, it'll generate different random data. All right, I see Kartik has figured out holding down F9. Right, so you can see that different random data gives us different histograms, different dot plots, but they all have an approximately even number in each. So now we can look at some data that's not just randomly distributed. It has what's called a normal distribution. And that's something that we won't go into too much, but it is kind of interesting to look at. So copy that column L and paste it into A. And now we see that the data tend to be centered around 0.5. And you can keep hitting F9, and that will give us more data. Right? So if you look at the individual values, you'll see that there are a lot more values between, say, 0.4 and 0.6 than there are between 0 and 0.2. Okay? So that's what this histogram shows us. It shows us that we have more values in the center. And if you look at the standard deviation of this normally distributed data, you'll notice that it has a lower standard deviation because it's less spread out. It's closer to the mean. Does that make sense to everyone? So we can try it now with what's called a skewed distribution. So again, we're going to copy column M, paste it into column A. Now what do you see here? Can anyone make any observations as to how this data differs from the first two we looked at? Take a look at the overall shape of our histogram. Yes? Okay, so there's nothing greater than 0.7. That's good. So we have what's called a different range. So our data are all between 0 and 0.7. Yes, Andrew? Pardon? What about 8, 9, and 10? Sorry, Andrew, I didn't catch that. Okay. You'll notice something else about it. It's not symmetrical. All of our other histograms were approximately symmetrical. This is not. Within the range that we have, which is 0 to 0.7, we have more data in the 0.7 end of things. So that's what's called a skewed distribution. Skewed meaning basically not symmetrical. Does that make sense? So this even line, as we saw for the random data, that bulge in the center, as we saw for the normal data, and this skewed distribution is all what we call the shape. And so in this case of the skewed distribution, it tells us that we have more data in the upper part of the range. So now we can look at something else. So in column N, we can copy that and paste it into column A. This is what's called a bimodal distribution. Now, when you learn about mean, was anyone taught about median and mode? That ring a bell to everyone? So who can tell me what the mode is? Yes, I haven't heard from you.
Number that appears the most in a set of data.
Right. So the number that appears the most. So in the case of a histogram, what the histogram tells us about the mode is where the maximum of it is, right? So in our normal distribution, we had that peak at 0.5. That tells us that was the mode. In this case, we have 2 peaks. And that means that we have what's called a bimodal distribution. It has 2 modes. Is everyone following along so far? Yes. Are you having trouble? Okay, so what you have, what I'm going to get you to do is reload this data set and copy it in again, because you've changed something that, that caused it to invalidate one of the formulae. So now let's look at something that you guys are going to be able to relate to a little bit more. Has anyone ever seen Michael Jackson perform Billie Jean? That's the one that he famously wore the one white glove in, right? So some of you, put your hand up if you know what I'm talking about. All right. There is an interesting data set on the web that's actually tracked the location of his white glove in one fairly famous recording of that performance. And the X position, so the distance horizontally of the white glove on the screen, is listed in column O. So we can copy that and paste it in. And we can look at the distribution of where his white glove happens to be throughout most of the performance. So we can see 2 peaks. So what does that mean? Anyone remember the term I used to describe that? Bimodal, right? So it's bimodal, so it means that his white glove tends to be either in this section or this section, but not too much in the middle, right? And we also notice that it's skewed in one direction. So it's skewed, which tells us that it tends to be more towards the left than towards the right. And we can even go ahead and plot this against time. So to do that, select column A once you've pasted the white glove data in. Go to Insert, Line, and the first one. And this actually shows us a graph of the location of his white glove throughout the performance. This isn't actually the whole performance. This is only about 30 seconds of it. But you can see how it tends to be more towards the left, but there's a little bit on this right half as well, nothing in the middle. Right? And if you look back at the histogram, you also see that he tends to keep his white glove in the center of the screen. Now, he's actually dancing around, moving all over the stage. The reason it's in the center is because the videographer keeps it in the center. So kudos to Matt for doing that, or Matthew, sorry, for doing that for us. And as you can see, the videographer for Michael Jackson also did a great job of that, right? So that sort of shows us a real-world example of why all this stuff is useful. Does any of this not make sense to anyone? Does anyone have any questions so far? Everyone still following along, still caught up? All right. And finally, we're going to take a look at some traffic data. So we're going to look at the delay on the 404 northbound between the Gardner and Bloomington Road. This was, I believe, 2 Tuesdays ago that this happened. And this was at the evening rush hour. So we're going to paste that column P in, and we can get rid of this. And we can now see our delay, histogram, and dot plot. So can someone tell me something about this data, given what we're seeing? Any insights? Anything you think this means? Andrew, do you have something? Just stretching? Pardon? Nothing above 0.7. That's good. So I should actually point out what the range means here. All of the data are still between 0 and 1, and this is how much of a fraction of an hour the delay is. So you're right, nothing between 0.7, so it's all less than about 35 minutes delay. So that's good. We see, except for this first point, we see a fairly nice distribution here. And that nice distribution is skewed. So it tells us that the delay tends to be more than less, except that sometimes the delay is very much less. So what this tells us is that we have normally fairly good conditions, a fairly low delay, just a couple of minutes. And then sometimes something happens like an accident, or in this case, rush hour starts, and cars suddenly start piling up and piling up, the delay increases very quickly. So there's not too much time that it stays in this transition phase of just a couple minutes, and then it hits this congested phase, and it stays there for a while before heading back down and being very low delay. Okay, does this make sense? Does anyone have any questions on this? Good. So we.
Either good or really bad.
Pardon?
So it's either good or really bad.
Yeah. Yeah, so that's what this data shows us, is that on that particular afternoon, there wasn't too much transition time. It was either nearly free flow conditions or very delayed. Okay?